Ready for part two, and this is going to be dealing with the car at the bottom of the ramp going into that little box, and then the little box sliding a certain distance. So that's what we want to concentrate on now. But I have put in some additional information for you, a summary of what you should now know. So you should now know that a change in momentum is going to be caused by a force acting over a certain amount of time, and then that was called an impulse. You should also know that conservation of energy meant the energy you start with has to equal the energy that you end with. And then we also learned that there were two kinds of energy. You had potential energy, which depends on position, and then you also had kinetic energy, which depends on the speed of the object. So question number 9. At the top of the ramp, the car had what kind of energy? So you got a 50-50 shot. So fill that blank in. As the car went down the ramp, this energy was converted into what kind of energy? Okay, now at the bottom of the ramp, the car slid a certain distance before coming to a stop, and you should have recorded that distance in your chart. Okay, what is the value of the car's final kinetic energy after it has slid that certain distance? Okay, so I'm looking for a number. So what is the number for the kinetic energy of the car when it's in the box and then the box comes to a stop? Pretty easy. Okay, what is the value of the car's final potential energy? Now, it has no height now. It had height when it was up here, but then when it slid down to here, the height went to 0. So that tells you that its potential energy is, go ahead, put that in there. And so now, where did the original energy go? So it had original energy when it was up here. And then you let it go, and then it goes down to here, and it still has energy, right? Because it had kinetic energy. But now, when it's over here, it comes to a stop. So where do you think that energy went? What was it turned into? Okay, think about that. Take your hands, rub your hands together. What do you feel? Okay, so that should help you a little bit there. So where did all of that energy, what was it turned into when that thing came to a stop? Okay, now here is work. Work is given by the letter W. It is, it's not a type of energy, but it is the energy that is either given off or the energy that you put into something in order to move it. So it's energy in transit. But we can just kind of call it energy. So W is going to be work. Notice it's got the units of energy, which is called the joule. So J for joule is the official metric unit for energy. And it's the energy that's going to be transferred from an object due to a force and is given by this formula. So W equals F times R, where F is the force that's being applied, and then R is the distance it travels parallel to the force. So in our case, it went down the ramp, it went sideways a certain distance. That's going to be the letter R. And then F is going to be this mysterious force, which you know what it's got to be. I hope you know. So what's the force that's slowing it down? And then, so that's question 13. So what was the force causing the car to slow down? Okay, now we're going to go back to your table. And so look at your data table, and you're going to look at going from 10 centimeters to 20 centimeters. So look at those two rows on your data table, the one for the 10 centimeters and the one for the 20 centimeters that the height was released from. Now, do you notice if you go from 10 to 20, what are you doing? If you're going from here up to here, you're doubling the height. So the height that the car is being released from is doubled. So by what factor does this increase the energy? So now I want you to, if you go back to your data table down here, there it is. So I want you to think about, if you double the height, what would that do to the potential energy? So the potential energy depends on the height. And if you double the height, what will it do to the energy? So that's the question that you need to answer there. Okay, so that's what I mean by what factor. So is it 3 times? Is it 2 times? Is it 5 times? That's the answer that I'm looking for here. Now, by what factor did it change the stopping distance? So look at the stopping distance for 10 centimeters, the distance that it slid, and compare that to the distance that it slid for 20 centimeters. So look at this number right here and compare it to this number right here. Okay, that's going to be that's significant. So you notice that if you double the height, you're doubling the energy. And then where's that energy going? That energy is going into the sliding. And so the sliding thing is going to be the distance that it's moving. So if you have double the energy, you'll have double the distance that it's going to slide. So you're going to fill that in here. Okay, now here's something that's kind of interesting. Look at the velocity at the bottom of the ramp that corresponds to the 10 centimeter height. So for 10 centimeters, look at the velocity it had at the bottom of the ramp. Now you can use either the velocity that you got, that it should have had if there was no friction, or I think you can even use the other velocity, which was the actual velocity. So it doesn't really make any difference which velocity that you're looking at. What height corresponds to doubling the velocity? So look at your velocity and then look at your data that you've got here and look at what height is necessary in order to double the velocity. Okay, so that's going to be kind of interesting because a lot of people are going to think that if you go 2 times as fast, then you're going to have 2 times the energy. And that ain't true. Why? Okay, let's look at this right here. Okay, so this involves the energy and the speed. And so a lot of people think, so I'll just put my hand over that squared thing. Well, you can still see it, but if I was to double the speed, it doubles the energy. That's not true, because you got to take the speed and do what with it? And then that's going to do something to this energy over here. Okay, so that's the point that I'm getting at there. Now this can be really important because this is related to stopping distance. And then by what factor does it increase the stopping distance? So if you were to double the speed, we know that's going to double the energy, And so then what do you think it's going to do to the stopping distance? The distance that the box is going to slide. If you're doubling the energy, what's it going to do to this thing over here? And then if you're doubling the speed, then that's going to do something to this energy again. It's not going to be double. And then this thing over here is not going to be a 2. It's going to be something else. Who cares? Okay, so the point is that let's say that you're in a car and you're following a tractor trailer. Okay, now you know that if you're going, let's say, I need to make up a number here. So United States, 30 miles an hour. In terms of kilometers, 40 kilometers per hour, I think, maybe, something like that. So you people in Europe, you know what I'm talking about. So here in the United States, let's say that you're going 30 miles per hour. You know that you need to have a certain amount of distance in front of your car, between your car and that tractor trailer in front of you. Because if that person slams on their brakes, you've got to have enough time to slam on your brakes and not skid into them. So that means you need to leave a certain amount of distance between your vehicle and the truck. But now, let's say that you're going twice as fast. So you're going down the highway at 60 miles per hour instead of 30 miles per hour. How much stopping distance do you need to have? So there's a lot of people that would say, well, double the speed. I guess that means I need to have double the stopping distance. No, that's not right. So we now know, based on what I was just talking about, you don't need to have 2 times the stopping distance. You need to have, say it, 4 times the stopping distance, because you got to take that 2 times for your speed and square it, and so 2 times 2 is 4. So you're going to need to have 4 times the stopping distance. All right, so that completes part 2. So now we're ready for part 3, and we're going to look at the ballistic pendulum. Now this parts 3 and 4 are not going to take nearly as long as parts 1 and 2. Okay, so don't get too worked up over that. So let's take a break and we'll come back for part